Okay, as we already learned from the announcement, this is the last talk of today, and the speaker is David Burns, and he will speak about Annihilating Tate-Shafarevic groups.
Thank you. Is this working? The microphone is working. Okay, great. So what I am going to talk about today is really informed by main conjectures in non-commutative Iwasawa theory, and so I first of all want to give a quick review of what a main conjecture looks like. Maybe I'll give it here. So we heard earlier in the week about such conjectures, but let me just recall for you the shape of such a thing. So if for certain p-adic Lie extensions, so Galois extensions of number fields, so P is a prime, lambda G is the Iwasawa algebra of G, and certain localizations, I'll just call them lambda G prime, of lambda G, the following scenario occurs in arithmetic. So one has a complex of lambda G modules, with the property that it's perfect, and such that if you extend scalars to the localization, it becomes acyclic. So this scalar extension annihilates all of the cohomology modules of this perfect complex. So under this kind of situation, there's a natural way to associate an Euler characteristic. Let me call it the refined Euler characteristic of C, such a complex, in what's known as a relative algebraic K group associated to this scalar extension. And from the general theory of relative algebraic K theory, this group is the image of a map from a Whitehead group of the localization. And a main conjecture has the following shape. There exists a characteristic element of the complex C, so a pre-image under this connecting homomorphism of this refined Euler characteristic with given interpolation properties. So the conjecture asserts for a given arithmetic complex C, there exists a characteristic element, so a pre-image under the connecting homomorphism of its Euler characteristic, with given interpolation properties. Okay, that's what a main conjecture, the basic shape of such a thing. So one even knows now a strategy for proving such a, at least there is a common strategy for trying to prove such conjectures. And that is basically, first of all, one has to establish in a given arithmetic context that certain groups are torsion, and we heard the first real examples of this kind of phenomena being proved. Torsion in an appropriate sense, torsion with respect to this given localization. So let me just say, prove that this complex is acyclic, which is hard. Then the next step would be to prove we have a given non-commutative, non-abelian rather, Galois extension, to prove sort of classical main conjectures in a classical sense, for lots of abelian subquotients of K over K. And then 3, recognize the condition on the p-adic L functions which arise in these abelian subquotients, that they should all arise from specialization from a given element constructed with respect to the initial non-abelian extension. So this, in the cases where people have been successful, such conditions are mutual congruence relations. So describe and prove congruence relations between the p-adic L functions in 2 which are equivalent to them all arising via specialization from a given non-commutative object. Equivalent to existence of, let's just call it a non-commutative p-adic L function. So such a strategy has been proved successful in an increasing number of cases, and work in progress. Hopefully, we'll establish it in increasing generality. I simply want to point out that we heard already earlier this week that this, for elliptic curves, is the assertion that a certain Selma module is torsion with respect to this localization. It's very hard to prove. And number 3, recognizing, describe, and prove these congruences is extremely difficult. In any generality, in any very general kind of context of a p-adic Lie extension, we still don't know what the congruences are, and we certainly don't know how to prove them. So that kind of background motivates what I want to talk about today. I want to talk about sort of an interpretation of these congruences, or slightly weaker versions of the congruences, which is very explicit, and in which, in some cases, one can actually prove. So that's what motivates the discussion. Yeah. So more concretely, the aim is to interpret these congruences as constructing annihilators for Tate-Shafarevic groups. By Tate-Shafarevic groups, I mean the Tate-Shafarevic groups in the sense of Bloch and Kato, of let's say Bloch-Kato, Tate-Shafarevic groups, and then I'll explain as I go along why that's really interpreting these congruences in a rather concrete way. So some notation that I'll use, I have a number field K, a prime P, which I guess is odd. I have a p-adic representation, so finitely generated torsion-free ZP module with a continuous action of the Galois group of K and ramified outside sigma. Sigma is a finite set of places containing the Archimedean places of K, containing V dividing infinity, union V dividing P. And the Tate-Shafarevic group, as I say, is the Bloch-Kato Tate-Shafarevic group of this p-adic representation T, which I won't recall, but I'm simply going to tell you, for concrete examples, what it actually is. Facts that we'll use, apart from its definition, are that this is finite, and that there's a pairing proved by Matthias Flack. If you take the Tate dual rather of T, it's isomorphic to the Pontryagin dual before you took the twist. So this is Matthias Flack's.
You mean this is Shah, so to speak, modest divisible subgroup?
Yes. Yeah. This is the generalization of the Cassels-Tate pairing proved by Matthias Flack.
But this is only the p primary part.
This is the p primary part. Yep. T is a ZP module. So the examples I have in mind, and that we'll say something about, sometimes unconditionally, that if T is ZP1, for example, to make the computation, it's actually a computation in Matthias's original paper. This is just the class group of the field, okay? Obviously, it's p primary part. So this, by his pairing, tells you that Shah of ZP is just the Pontryagin dual of that. And you can go on. If you take R an integer bigger than 1, this Shah is always a natural object. And here, at least if the Cullen-Lichtenbaum conjecture is true, it's what's known as the wild kernel of higher algebraic K theory. Algebraic K theory. Doesn't matter what that is, I'm just telling you it's natural. So this is modulo Cullen-Lichtenbaum, being valid for K at the prime P and with the integer R. And another example that I'll mention, of course, is that if E is an elliptic curve over K, then Shah of the Tate module of E identifies with the p primary part of the classical Shah at least if the classical SHA is finite. So all well-known examples are just motivating the general theory that I'm going to set up. I'll describe a general theory and then apply it in the cases 1 and 3, just to see what comes out. So actually, what underlies what I'm doing today is an observation in homological algebra, which I'd like to tell you about first. And this observation is really a slight improvement upon an idea worked out in the commutative case by a recent PhD student of mine by the name of James Barrett. So this is really an idea of James Barrett being slightly improved. So the first section that I'd like to talk about is, as I say, just homological algebra of a rather technical nature. Now, ideally, we're going to work on the level of Iwasawa theory, but everything via a passage to limits can be deduced from a case of finite groups. If you can do the case of finite groups, that's somehow more difficult than the Iwasawa theory in many cases. This is a finite group. That's where I'm going to start from. I have an order over Zp, which is actually a direct factor of the p-adic group ring. And this spans an algebra, which is Roman A. And whenever I have a ring, Z of that ring will mean the center. That's the kind of notation I have. So which complexes am I going to study? The complexes I have in mind are clearly going to be perfect. That's what they are for the main conjecture. And at this finite level, they will be perfect again. But they have some additional conditions. So I'm going to call definition, so let's say a complex of A modules C, let's just call it admissible for now, if it satisfies 4 conditions. Firstly, it's perfect, which means it's quasi-isomorphic to a bounded complex of finitely generated projective A modules. Secondly, if you extend scalars up to the algebra, this is a perfect complex over the algebra, so it has an Euler characteristic. That Euler characteristic should be 0. Has 0 Euler characteristic in the Grothendieck group of the algebra. Thirdly, our complex C should be acyclic outside 3 degrees. 3 consecutive degrees, which we'll just take to be 1, 2, 3. And fourthly, in degree 1, the strange one, the cohomology of C in degree 1 should be Zp free. So I won't properly motivate this except to give some examples.
You mean Zp torsion free?
It's finitely generated. Yeah. Zp torsion free, if you like. So the examples are obviously motivated from arithmetic. That if we have our p-adic representation T and base change it through a finite Galois extension with group G, the compactly supported cohomology is actually admissible. I'll motivate it simply by virtue of examples from arithmetic. So the examples come from this situation. Let's take K over K finite in Galois. Let's let G be the Galois group. Let's say this is unramified outside sigma. the same sigma we had before. So then, if you take a compactly supported cohomology of the restricted Galois group with coefficients in T base changed, this is admissible. So it's certainly very well known to be perfect. It's very well known that if you extend scalars to QPG, it has zero Euler characteristic. Cohomological dimension arguments give you very quickly it's acyclic outside degrees 1, 2, 3. The only sort of non-obvious one, if you're looking at the theory the first time around, is why is H1C, let's say, of T torsion-free, and the point is that H1 of C is H0 of T tensor QP mod ZP, and H0 of C for any sheaf is 0. So, compact support cohomology works under certain hypotheses. If you have an abelian variety over K, and you take a suitable Selmer complex of the Tate module of the abelian variety, base change through this finite extension, that's also admissible. So the two main examples we'd have in mind if we were doing Iwasawa theory. But then the third point is important from the point of view of making calculations in this category, and it's a very easy point. If I take a complex which is admissible, and I take its linear dual in a natural sense, so the linear dual would be the R hom over Zp of Z of C rather into Zp. But because I've insisted they're all acyclic outside degrees 1, 2, 3, you have to renormalize this, I think, just shifting 4 places. This is also admissible. So this is an important point when it comes to calculations, and it sort of it mirrors the fact that the Tate-Shafarevic group has this duality property. Okay, so there is a category of admissible complexes which arises quite naturally in interesting arithmetic contexts. If C is admissible, let's fix admissible. And what I'm interested in is then looking at an idempotent which annihilates all of its rational torsion. So this will be an idempotent of Roman A, the algebra, such that, so the Euler characteristic is 0 and it's acyclic in degrees 1, 2, and 3, which means that in degree 2 the vector space somehow is the sum of in degrees 1 and 3. So I'll just annihilate in degree 2. And then, so before I state the theorem, let me just make some observations. If I base change my C from the order A to the order A times the idempotent E, I'll call that CE. So that's a base change in the derived sense from the order A to the order AE. So this is perfect by standard nonsense. This time, of course, over AE. And such that if I now extend scalars up to the corresponding algebra, because I've annihilated the algebra rationally, this CE is already acyclic, such that CE tensor ZPQP is acyclic. Or if you like, tensor over AE with Roman AE is acyclic. So now I have the setup for a baby main conjecture. I have a situation where I have a perfect complex over AE, such that rationally it's acyclic. And when I recall for you the shape of a main conjecture, what that would tell you would be that there is a refined Euler characteristic of this complex, this time in a relative group for the order with the idempotent and the algebra with the idempotent.
the E a central idempotent?
Yes, it is. Thank you. This has a map from the corresponding Whitehead group, which at the finite level is now via the reduced norm map, isomorphic to the center of AE multiplicative. And then the shape of a main conjecture would be talking about a characteristic element of this complex in this group. So now what I'll talk about is a characteristic element in the center because they're isomorphic at a finite level, and I'll call it LCE. So LCE is a characteristic element at this baby level of a main conjecture, if you like, for the refined order characteristic of this complex CE. Okay, so now I can state the homological algebra theorem. We have enough setup. So the theorem states the following. So we've got C, a perfect complex, E, a central idempotent, and the characteristic element for the base change complex CE. So it says if I take Y, which is a central annihilator of the torsion subgroup of H2C, and X is any element of the center of the order which is invariant under multiplication by the idempotent. Actually, I think I mean that. That's the same thing, sorry. Then we can construct annihilators using the characteristic element for the torsion of H3, which somehow will be arithmetically very interesting. So then the characteristic element multiplied by a weighted sum. So here I'm summing over all characters of G. I take the character value of X raised to a certain exponent, which I'll explain in a moment. I take the det over chi of Y. So this means evaluate Y at the, take the corresponding representation of character chi, hit it with Y, you get a matrix, take its determinant. And this integer GC occurs again. I have a d chi and a projector chi, which I'll explain in a moment. So this rather complicated sum, multiplied by the characteristic element, annihilates the torsion in degree 3. Notice this is, of course, in the center of the order rather than the algebra. So in particular, it's saying that this complicated sum takes away the denominators of this characteristic element, and more than that, it not only lands in the center of the order, as an element of the center of the order, it acts on H3C, the torsion subgroup, and it annihilates it.
The torsion means P torsion.
Means ZP torsion. So obviously, you know, SHA will be somehow related to these things in arithmetic examples. So what are these numbers? Where, so GC, this is just the minimal number, I guess, of generators of H3, C as an A module, I've got projector chi, which is just the projector in the group ring. So the central idempotent of character chi, but then multiplied by a weighting factor, so you have no denominators. And then d chi, which is the only thing that's missing, is a certain multiple of the Schur index of chi. So this is E over qp chi, the degree of E over qp chi for any field E. So if you like choose the minimal possible field E, that over which the character chi can be realized, that will contain the field of coefficients, and that's the degree. So where chi realized over E And for a technical reason, E over QP is Galois. And finite, obviously. So in this sum, we have data coming from the annihilation of the cohomology in degree 2. You hit it with the representation, get a matrix, take the determinant of the matrix, raise it to a power. The character acting on anything in the center of A, invariant under the idempotent. You have a multiple of the Schur index, let's take it to be the Schur index, times the projector. Normalize the characteristic element by this rather complicated sum. And you have something which has no denominators and annihilates H3. So that's the theorem. And it looks a bit of a mess. So I'll make some remarks about it and then show you that in concrete examples it's actually not much of a mess. So the remarks are, you can apply the theorem, replace C by C star, as I commented. If you replace C by C star is still admissible. So that has the effect that E switches to, if you call it E hash if you want. So hash is the involution. So hash goes from the center, goes from, let's say, QPG to QPG, and is QP linear and inverts elements of G. That's because on the linear dual, of course, you put contragradient action. So if you switch C to C star, then E is simply replaced by E hash. If you compute cohomology of C star, it simply has the effect that H2 and H3 are swapped. The universal coefficient spectral sequence will tell you that the cohomology of C star in degrees 2 and 3 is the cohomology of C in degrees 3 and 2, at least the torsion subgroups. And the one more thing, if you take the characteristic element for the dual complex, in fact that's just the original characteristic element with the hash and inverse. So this comment is, if you replace C by C star, you get a theorem in which H3 and H2 have been swapped, which is also important in arithmetic. And the second remark is that if you look at what the theorem says, one of the things it says in particular is that this rather complicated sum, when multiplied by LCE, annihilates all denominators. So that's actually a statement, a congruence condition, on the different components of this characteristic element. So the theorem actually expresses an explicit consequence of congruence conditions between the different components as the characters vary. Components of the characteristic element. Remember, this is in the center of the order of AE, and that's contained in a product parameterized by certain characters chi, with values in, I guess, QPC.
So David, it's not just somehow removing denominators from the characteristic element?
No, it's doing much more. It removes denominators and then allows you to assert it actually kills a group that will be related to Schur.
So it's not like the classical Stickleberger case where
I'm going to say.
So in this statement, G was always finite, right?
G is always finite. One can pass to limits. Or maybe I'll mention at the end what happens if you pass to limits. But in some sense, the finite case is the most difficult, in a certain sense.
Number 1 for that L function, there's no E hash on the left?
Thank you, yeah. So it's expressing a rather explicit consequence of what amounts to the congruence relations that one must prove if one wants to establish the existence of a non-commutative p-adic L function. In some sense, what this is saying, it's no wonder they're difficult, because it's taking a characteristic element and observing with relatively little work that it's going to annihilate things like Schar in a rather complicated context. So what are the applications? Of course, the applications in arithmetic would be when C is an arithmetic complex, as the examples I had before, compactly supported cohomology of a suitable module, or Selma complex of a suitable module. LCE then becomes an element which conjecturally interpolates values of complex L functions or p-adic L functions as chi varies over the characters of the group. And so this weighted sum is a weighted sum of values of L functions, either complex or p-adic, conjecturally. And the conclusion is that they're going to annihilate some arithmetic module. So there's a rather general approach to this, a rather general theory in which one relates modules of this kind, if C is compact support cohomology, for example, relating the torsion in H3 to the Bloch-Kato Schar, which is a question simply of making some computations in arithmetic duality. I wish somehow to suppress that aspect. If I have time at the end, I'll describe how it works. I'm just going to try to convince you that this rather messy formula actually is not so messy. So I'll try and do that via a series of examples. The first example I'm taking is just ZPG, so if you like, T is ZP. And my G, if you recall in the examples I had, was the Galois group of a finite non-abelian Galois extension. So in this case, one can actually prove enough of the finite level main conjecture to make this conclusion unconditional. If one works harder, one can even improve slightly the conclusion of this theorem. And you get this theorem, which is in a paper that I wrote jointly with Henri Johnston. And I'm going to give you the cleanest possible version of it, so I will impose some hypotheses. So entirely for simplicity, there is a version of the theorem without these hypotheses, but for simplicity, assume that P is unramified in the top field over Q, which is rather strong, but as I say, it just makes the formula neater. And the second one is that all inertia groups in G are normal, which again is not likely. It's not always satisfied, but again it just makes the formula simpler. So then what does theorem 1 tell you? So it tells you this rather neat formula. If you sum over all non-trivial characters of the group, and this is the value of the Artin L function, the untruncated Artin L function, the complex conjugate character chi bar, evaluated at 0. You have this sort of Schur index number, and you have the projector at chi. So this sum, so it not only has at P no denominator, but actually annihilates the class group. At least the P part of the class group. So this is what John was referring to. So this is an unconditional theorem. The proof of the theorem involves applying theorem 1 with C equal to this complex. So one has to compute what the idempotent E is. One then has to decide how much of the main conjecture one needs to be able to replace the conjectural characteristic element by an explicit formula. So the proof amounts to applying theorem 1 plus observing it's enough to know the main conjecture, I'll call it the main conjecture. This is, of course, at a finite level. Modulo a very difficult subgroup of the relative group, namely its torsion subgroup. It's an abelian group, and it has a torsion subgroup where all the difficulty lies. And in fact, if one makes some if one goes to some effort to get this version out of theorem 1, it's enough to prove the main conjecture modulo a certain subgroup, and then one can actually prove it. Prove this approximation. So you have to do some arithmetic at the end. So of course this is looking like it amounts to proving a big chunk of a non-commutative main conjecture at finite level, but of course I should just hazard some caution, because if you look at this sum, this value is very often 0, of course. In fact, it's going to be 0 if you have, for example, an Archimedean place splitting. Then the order of the L function at 0 will be greater than 1. So it means you can't have any Archimedean places splitting, so it means you're totally real or totally complex. And then it's easy to reduce to the case that chi is primitive. But then if you chase through again the order of vanishing formula, you're not just totally real, or rather totally complex over totally real, you're actually a CM extension, with a single complex conjugation. So then you can apply some Bauer induction type arguments and chase it down ultimately, because one has observed that one can ignore this group, to a situation where one can actually prove the relevant main conjecture, which of course in this case is the classical main conjecture. So it's a rather nifty way of avoiding the hard part. You still have some arithmetic to do, but out of it you get some very clean statement. If I specialize to k, small k, equal q, and g to be abelian, as John referred to, I just get a weak version, a slightly weak version of Stickelberger's theorem. So it's a slight weakening of Stickelberger. Which is not so bad, but there's no reason why I should take k to be q. If I just take k to be totally real and g to be abelian, remember the theorem is unconditional, so actually what you get is a slight weakening of Brumer's conjecture. So you actually prove unconditionally a slight weakening of Brumer's conjecture. Brumer's conjecture is just a generalization of Stickelberger's theorem to the context of a totally real base field. Of course, there's still some work to go to prove Brumer's conjecture in full, but the point is somehow that I wasn't aware of any unconditional statement of this kind. So this theorem 2 is the first example of theorem 1, this rather messy theorem in homological algebra, being applied in a concrete arithmetic setting. But of course, as I said, it doesn't really tell you much when the top field is totally real, because then all of these L functions will be 0, and the conclusion is that the 0 element annihilates the class group. But if you recall this duality isomorphism of Flack, if we want to study the class group, there's no reason to fix attention on ZP. We could switch and look at ZP1, and that rather nicely removes that obstacle. So if you switch attention from ZP to ZP1, the Tate-Shafarevic group that we're going to annihilate ultimately hasn't changed. At least you get the Pontryagin dual of it, so the annihilation statement changes in no important way. And you can see what happens here. This is a situation, of course, where the top field is totally real. For this to make sense.
Sorry, did you say something in general about how this H3 relates to the
So I haven't yet. But you're right. I'm annihilating H3C torsion according to theorem 1, which is sort of a messy kind of thing with no arithmetic significance. But what you prove, for example, in this context, is you can construct a surjection from H3C torsion to the relative Tate-Shafarevic group, which in this case is the class group. You know, well, the idea that there's a surjection from H3C, a compact support cohomology, to the Tate-Shafarevic group is general. So as I say, I'm just trying to convince you that this statement isn't as messy as it looks. So theorem 3, if K is the top field is totally real, and I'm going to assume Leopold for the top field at P, but actually for a reason I'll explain in a moment, I don't think I have to. So then again you get a very, very clean statement. If I take any element in the center of G, which isn't the trivial element, then I have a sum over all characters chi, non-trivial characters chi. This is now the sigma truncated p-adic L function of chi bar evaluated at 1. I'm going to get some formulas of this type coming in, and in fact you get chi of sigma minus 1 cubed is a factor. You get the Schur index factor, you get the projector, but then you have this sum. This sum annihilates the class group.
There is no sigma, it does nothing.
Yeah. So again, a rather clean statement, and there are no conditions on G. It could be a very complicated finite non-abelian group. And so this is a particular specialization when you plug C equals this complex and make some calculations of this formula. Sorry, yeah, no, that's right.
And with not a vague generalization, I don't know how to make it finite in your setting, but where you look at the Galois group on ramified outside E rather than
Actually, that's actually what, of course, what comes out of the theory. Yeah. So just to pick up John's comment, actually, one produces annihilators of the Galois group over maximal pro P abelian extension of big K and of small k, I guess, and ramified outside sigma over K, and I guess maybe the torsion subgroup. But of course, there's an obvious map from this which doesn't quite pick up all of the class group, but then that's why you get an extra factor of this, which is all very explicit. If one specializes in this case to K equal Q and G cyclic, this is a totally general statement, but if one specializes to K equal Q and G cyclic, then actually what one picks up is an annihilation statement about the class group of a totally real field, or if you like, about the Galois group of the maximal extension and ramified outside sigma of this field, and you recover all results of Gra and Oria. They had a series of papers where they construct, in this context, annihilators of these Galois groups, and so the theory just shows how they fit into a general non-abelian picture. This, of course, is no longer the complex L function, it's the p-adic L function, and this theorem is unconditional, at least modular Leopold. Why you should get rid of Leopold is the following. If Leopold fails, if the chi component of Leopold fails, this value is 0. So if instead of this sum, I somehow summed over all characters chi, which were non-trivial, and for which the chi component of Leopold was valid, the sum doesn't change. So one should be able to remove Leopold. And lastly, a comment. There's a conjecture of Serre which expresses this value at s equal 1, which is the leading term if this is non-zero, of the sigma truncated p-adic L function in terms of the value, or the leading term rather, of sigma truncated complex L functions. That is a conjecture, the p-adic start conjecture. If that was true, then you could reinterpret this in terms of complex L functions, but I won't mention that. Again, why is this true unconditionally, at least modulo Leopold? The same observation as before. To deduce this explicit statement from a main conjecture type statement, one can actually ignore the very hard part, in some sense, of the main conjecture. The torsion subgroup of the relative algebraic K group can be ignored, which allows some Brownian induction techniques to be applied, which is why one can prove enough of the main conjecture to make this depend only on Leopold, and hopefully not even on that. Okay, so now the case of elliptic curves. This is obviously a machine that one can apply in interesting arithmetic contexts. So the last case is the case of elliptic curves. So here in this setting, so P is good ordinary reduction. I guess I'm assuming that Sha E over K is finite. E over big K is finite. So take an elliptic curve for which that is true. And the prime P for which there's good ordinary reduction for E. So our main conjecture has been formulated. I'm also going to assume, because it makes the theory work, that P doesn't divide the order of torsion in E, the mod of A group of E over K. That's a finite group and P doesn't divide its order. So in this setting, you could of course apply the whole theory in the sense of the Tamagawa number conjectures, where the complex would be the compact support cohomology. So I guess sigma also contains the places of bad reduction for E now, but I won't say that. You could base change the Tate module through this finite Galois extension. This is a perfect complex. We know it's admissible. But then if one makes the computation here, actually what happens, if you try to annihilate the second cohomology group, the only idempotent that does it is 0. Because the second cohomology group, if you make the computation, contains the tangent space, and you've base changed through the Galois extension, so the tangent space is somehow a free QPG module. So compact support cohomology won't give you anything interesting. You can apply the theorem, but the only idempotent, if you take C to be this complex that works, is the 0 idempotent. So this is the reason you switch attention to the Selmer complex, which in this setting is a much more useful object. So the Selmer complex is admissible, I said, under some conditions. The conditions are precisely P doesn't divide the order of torsion in the top field. This forces implies this is admissible. So if that's not true, it's simply not admissible. You can't use the general theory. But if you assume that the torsion P doesn't divide the torsion subgroup upstairs, the general theory applies. So if you apply the general theory with this complex, what comes out? So what comes out in this setting is this result. So with the conditions I have here, an elliptic curve, good ordinary reduction at P, Sha is finite, and I'm assuming, so then I'm assuming it's not going to be unconditional, but if you assume the so-called local and global Tamagawa number conjectures, as formulated, for example, by Fukaya and Kato, and I don't mean, of course, for every motive, I just simply mean for E at P. for those who know the paper, and the order is, of course, here ZPG. Then we have one of our sums, just applying the general formalism of the theorem again. The sum over all characters of G, you get the sigma truncated twisted Hasse-Weil L function evaluated at 1. You have certain periods here, and you have a certain fudge factor depending on chi. This fudge factor is just the evaluation of Euler factors at p at the unit root of the polynomial that defines the Euler factors. I'll write it down if I have time later on. So this sum, this weighted sum, has no denominators, but also annihilates the Tate-Shafarevic group. And if the Tate-Shafarevic group of E over K is assumed to be finite,
There should be a PR chi there or something.
thank you, and a d chi and a PR chi. So this is E over K, and it's P primary part. And again, this is how does this come about? Of course, it's an application of theorem 1. And then, so again, let me stress this is G is any finite group. So it's theorem 1 plus. So here there was a reduction before modulo the torsion subgroup. In fact, one can make such a reduction, and one has to change slightly the hypotheses. They weaken. You don't need the local and global Tamagawa number conjectures for the full thing, only for pieces, but it's still conjectural, of course. But then the key thing I want to say here is that if you look at one of these Selma complexes of as defined by Jan Nekevar, you don't actually get the Selma module as its cohomology. So you have to relate, I guess it's H3 C torsion to Shah in the sense of Bloch-Kato of TPE ZPG. But as again, that's I find a fairly general computation in arithmetic duality, and it's certainly true. For example, this computation is certainly true for any critical motive. So in particular, an elliptic curve will make it work very smoothly, but any critical motive will do.
And that uses finiteness of Shah?
Yes, simply because I'm writing down the classical Shah here. You only use it when you want to write down in the theorem Shah, the classical Shah.
But not that low state.
No. This is purely p-adic.
Needs the Tamagawa number conjecture just for the motive of E, or also for the twist by the characters chi?
Well, if I put E over the big field. Right, so I've been as safe as possible. But by a reduction argument, one needs much less than that. One really needs, by a reduction argument, H1E over the bottom field, tensor chi, a certain chi. This would be enough. But it's still conjectural, of course. But anyway, the fact is that this is totally explicit. I haven't told you the fudge factor, but it's totally explicit. And the conclusion is that this totally explicit sum, which is just an evaluation of truncated Hasse-Weil L functions, annihilates Shah, which would be difficult to prove, but shouldn't have any denominators, which would be easy to spot. And you can just run it and compute it and check whether it has denominators. And so this kind of observation at least gives some really concrete consequences of the main conjecture, rather subtle consequences. Not having denominators amounts really to congruences between the different components in this sum. So the fudge factors I'm just going to actually not mention, but they're not important. If you specialize, just as we were doing before, to k equal q and g abelian, what you get is the statement that this sum is annihilating a Shah is really that the refinement of the Burt-Swinnerton-Dyer conjecture that was formulated by Mazur and Tate. So what's going on here actually is that Mazur and Tate in their paper actually ask for what they call a strong main conjecture. They conjecture that some elements constructed using modular symbols rather than just the values in this case should annihilate. Actually, they conjecture it lives in the fitting ideal of Shah, and they say it would be nice to have a convincing strong main conjecture where you construct an element which should generate the fitting ideal. So actually one of the things that I haven't talked about is that this theorem actually improves so that you get an element on the left-hand side which is a generator of the fitting ideal of Shah, or in fact of the Selmer module. And in the non-abelian theory, there is a natural analog of the notion of fitting ideal, and this element generates that natural non-abelian analog of the fitting ideal also. So you have not just a strong main conjecture that they ask for, but also a non-abelian version of a strong main conjecture. Alas, of course, the only evidence that for this kind of assertion is in the main, I mean, of course, there's increasing theoretical evidence for the main conjecture, but there's computational evidence for this sum not having denominators. And I'll just finish by saying that the computational evidence is due to Naviralakalu and also Werner Blei. And there's numerical evidence for saying sums like this don't have denominators. So the intention of the talk simply was to unwind some of the congruences that are very difficult to prove in non-commutative Iwasawa theory. So this theorem, which, as I say, in fact, in the abelian case is in James Barrett's thesis, and it's the natural non-abelian version of it, is a means of unwinding the congruences between the different components of a characteristic element and expressing consequences in some very clean terms. You have a non-abelian analog of Stickelberger's theorem, you have a version of Stickelberger's theorem for totally real fields, you have a non-abelian analog of the work of Mazur and Tate on the Burt-Swinnerton-Dyer conjecture, and these all come out of the congruences in non-commutative Iwasawa theory, which of course is why they're difficult to prove. But it's sort of rather neat to see it all coming out. Okay, that's great. Thank you.
Question.
Yes.
Why was it that the G of C's somehow never seemed to appear much?
For example, the G of C didn't appear in theorem 2 because I imposed some conditions on the inertia subgroups and hid some kind of clever arguments. They didn't appear in theorem 3, which is a more representative answer to your question, because if you take this complex and you compute it, it's acyclic modulo Leopold outside degrees 2 and 3. In degree 2 you have a Galois group coming out. In degree 3 you have ZP, so GC is 1. The minimal number of generators of ZP is an A module is 1.
So in the theorem you have the class group. So what was the class group coming out?
The class group here, In degree 2, what you get is the Galois group of the maximal and ramified extension of K and ramified outside sigma over K. This surjects onto the class group. Over K. Okay, so actually what you do is you construct annihilators for the torsion subgroup of that. That surjects onto a part of the class group. The bit that it doesn't kill, you kill by adding in another one of these. Because the bit that it misses is somehow acted upon trivially by the Galois group. So the cohomology in degrees 2 and 3, which are the only relevant ones. In 3 you get the ZP, in 2 you get this Galois group. So you apply the theorem, GC is 1. Applying the theorem, you're going to construct annihilators of this, or rather its torsion subgroup. The torsion subgroup relates to a certain bit of the ideal class group of K. Obviously it's much bigger, but it relates to the ideal class group. How much do you miss by? You show that you miss by something upon which the Galois group acts trivially. So if you just, this is why you get this rather surprising term here. You add in an extra sigma minus 1 to kill what you miss. Yes, thank you. This is pro P, and that's tensor with ZP, thank you. So they are there actually. It's just I work hard to hide them.
So what happens, David, if, which might perfectly well happen, that your ideal up there in theorem 4 is 0? All of those L values could be 0.
Yes.
But then but you're Shah non-trivial, and yet you said you get the fitting ideal of Shah.
No, what I'm saying is that you get the fitting ideal. Generally, if you want to make an assertion that you get the fitting ideal of Shah, actually what I'm saying is you get the fitting ideal of the Salma module.
Right, but it's non-trivial.
Which is non-trivial. So what it means is that the Salma module will be non-trivial in some components. Right? You have, let's suppose...
But they could all be 0.
They could all be 0?
Yeah.
In which case, this sum could be 0, and the assertion is it's contained in
So
the fitting ideal of Salma.
generate the fitting ideal.
Yes. Under some hypotheses, one can show it does. But those hypotheses would include, for example, an assertion about the idempotent E, and the idempotent E is measuring those components of the mod of group where you are 0 or not. So it's all wrapped up. And just to pick up what I was saying, you can have a fitting ideal of a module which has, it's infinite in some components, and it just means the fitting ideal in that component is 0. It lives in some component with an idempotent E. Yeah. So that it can generate that.
So what did you mean by the non-commutative analog of the fitting ideal?
So in this case, one can actually see it very explicitly. Because if you believe, or if you restrict attention to the formalism of Tamagawa numbers, and you have complexes like my C, so the choice of E guarantees that when you take CE, because in degree 1 this was torsion-free in the cohomology, when you project, if you recall this was this guy, it actually becomes a cyclic outside 2 degrees, 2 and 3. You compute the cohomology of this in terms of the cohomology of C, and because I'm assuming that in degree 1 the cohomology was torsion-free, this, which is a priori a cyclic outside degrees, I guess, 1, 2, 3, well, maybe even 0, 1, 2, 3, a priori, it actually becomes a cyclic outside degrees 2 and 3. So you have the cohomology in degree 3, and you have a perfect complex, which is like this. And what you can actually show is that Q is, you can realize this with Q being isomorphic to P. Okay, so you have an endomorphism here. And so H3CE is gotten, it's the co-kernel of an endomorphism of, let's say, a free ZPG module. and you could take the reduced norm of such an endomorphism over QPG, which is the analog of the det. In the abelian case, the det of phi would generate the fitting ideal of this module by the definition of fitting ideal. So you construct an ideal over the center of ZPG constructed by reduced norms of all such endomorphisms with this as the co-kernel. It's a natural analog of the fitting ideal, and indeed it obeys some of the properties of the commutative fitting ideals under scalar extension and everything. So this was worked out in a thesis of another of my PhD students, Andrew Parker. He had a non-commutative fitting ideal and related it to Tamagawa number conjectures. And what this theorem is really saying is that the L values generate this non-commutative fitting ideal. In the abelian case, the fitting ideal of this cohomology module. So it's really important, something I didn't mention, that in the definition of admissible, in degree 1, there is no ZP torsion. It simplifies things tremendously. And I was surprised that, this obviously has been known forever, that compact support cohomology doesn't have torsion in degree 1. But it's a really neat use of the fact, which, as I say, originates in James Barrett's thesis. It really simplifies things after base extension that you are acyclic in 2 degrees, outside 2 degrees. That's where it's used.
Last question.
Hi.
Can you just briefly mention the fudge factors in your last theorem? Are they integral or can they have denominators?
I think they could have denominators.
Can have denominators.
Yeah, absolutely. I mean, if you write them as a fraction, the bottom, there is a denominator to that fraction, and I don't see any reason why that denominator should be a p-adic unit. Yeah, I'm certainly not asserting that any individual term in this sum is integral. Just the sum miraculously works out so that you're not only integral, but then you can construct an annihilator for Schar. So, for example, suppose you show that this sum not only doesn't have any denominators, but is a unit of ZPG. Then you just computed Schar. Without ever computing Schar.
Okay, so then let's